No?
Yeah.
Okay.
She is moving a lot. Sometimes.
Hearty welcome to all fellows of the Indian National Academy of Engineering, our faculty, students and researchers from the state as well as from outside the state to this lecture, which is being organized by INA Bhubaneswar chapter, SOA University and IMMT Bhubaneswar. Today, this particular day is being celebrated by many institutions, including INA headquarters and IMMT Bhubaneswar. So people will definitely get distributed today, but doesn't matter. So as all of you know, today is a very, very important day for all of us, those who are in the field of technology and engineering. Say, on this day, that is 11th of May, 1988, we had a landmark in our technology development. On this day in Pokhran. This nuclear tests, underground nuclear tests, where series of them were carried out, and to commemorate that, we celebrate throughout the country this 11th May as Technology Day. So on this particular occasion, today, we have a very special lecture by Professor Charan Mohanty, a renowned person in the field of meteorology, atmospheric science, weather prediction in the country and also globally. So to introduce him, today of course we will not have Professor Ashok Mahapatra or IMMT director with us. So we'll straightway go into the introduction of the speaker and his lecture, and after that there may be some question and answer to be moderated by Madam Renu Sharma. Now, Professor Charan Mohanty, after working for 33 years, long 33 years in IIT Delhi, in very senior position and very prominent position in the atmospheric science department there, retired, and he is now the visiting professor in the School of Earth, Ocean and Climate Sciences in IIT Bhubaneswar. He also worked for a number of years in DST, National Center for Medium Range Weather Forecasting, as a joint director. He, under his guidance, medium range weather forecasting system was for the first time operational in this country in June '94. That was really a landmark day. He was in honorary capacity served as the Odisha Bigyan Academy president from 2013 to 2015. He had also served as Vice President of Indian Meteorological Society and Senior Associate of International Center for Theoretical Physics, ICTP, Trieste in Italy. Professor Mohanty is recognized for his deep understanding of fundamental meteorology, observational studies, numerical modeling. His outstanding researches led to set up several milestones, especially in the prediction of weather and climate, that have widely been recognized by the scientific community worldwide. The principal facts of his work facets of his work and research achievements include prediction of high impact extreme weather events such as tropical cyclones and associated with storm surges, understanding and prediction of summer monsoons processes, including heavy rainfall events, monsoon circulations, and associated monsoon events over India. His research work was also includes monthly and seasonal scale prediction of precipitation and temperature at the surface and application of the same to climate risk management in the fields of agriculture. Some of his work, he and his team's research work are translated to India Meteorological Department, transferred to India Meteorological Department and Meteorological Directorates of Indian Air Force for their operational issues. Actually, he's a very proud person of actually implementing so many of his things in Indian context. His illustrious teaching and research career over 48 years, during which he published about 325 papers, 70 technical reports, 43 PhDs, and still some of them are working with him for their PhD work. Professor Mohanty has been conferred with many awards and recognized, such as the prestigious Santi Swarup Bhatnagar Award, Bhatnagar Prize, and then also the award of the National Award for the Atmospheric Sciences and Technology, Biju Patnaik Award for Scientific Excellence, Sir Gilbert Walker Gold Medal, Samanta Chandrasekhar Award, Aeronautical Research Development Board Silver Jubilee Award, 12th Mosam Award, and of all, 4 National Science and Engineering Academies Fellowship. He is also Fellow of Indian Meteorological Society and Indian Geophysical Union. He has also been conferred with Odisha Citizen Award in 2018 in education. So the award list is really pretty long. And today, as we know, climate change and climate related things are they're possibly the most important events which may really change our entire society, our life, and even we do not know what is going to happen to our society as a whole. I think on this very important issues where actually the technology can help in a big way, Professor Mohanty has kindly agreed to give a lecture on climate change, extreme weather events, and technological interventions for sustainable development. So, a very important topic of the present time. So, I will now really request Professor Mohanty to make his presentation, and it will be followed by certain question and answers, vote of thanks, etc. So, Professor Mohanty, please kindly present your talk.
Thank you very much. So very good afternoon to everyone. My heartiest greetings to all of you on Technology Day. As it is exactly explained by Professor Damodar Acharya, this is a day to celebrate by all the engineers because it is for India is a proud day. And at the outset, I would like to express my sincere thanks to Professor Damodar Acharya for inviting me to give this lecture on this important day. So I will try to cover, I think in 1 hour, all my things that I am going to tell you. So I will start with an introduction where I will tell you the linkage between climate change, environment, and extreme weather events. Then extreme weather events, what it has linkage with the climate change. I'll briefly tell the concept of modeling. I'll illustrate you the importance of this aspect, how it is linked with the technological developments, and ultimately I will focus on few areas. Today I will focus on tropical cyclone and severe thunderstorms. So as you all know, climate models are now became most important tools for its increased efficiency and reliability to capture past climate more real with time and the capability to provide future climate projections. So observations for land-based weather stations in global network confirm that Earth's surface air temperature has increased by about 1 degree since late 1800 till today. As you know, that this dramatic change is very much linked with the technological developments. In fact, the second industrial which was in 1880, when we started using the coal as the source of the major energy for the industrial developments, power generation, and in various sectors for our comfort. Then we started releasing the greenhouse gases as the outcome of our technological innovations. You know that all innovations in technology has a good side because it gives you a lot of things. As today what we have, it is only due to the technological developments. We all are, I feel, in the best part of the evolution of our Earth system with all the comforts, and credit go to the technological developments. But aside, all technological developments, when we do use or misuse or use more extensively, it will lead to certain type of shortfalls, just like a nuclear energy to nuclear bombs. Same way, this is a thing where we are getting the energy for all our developments, because now we cannot imagine a day without electricity. We stay in the home without electricity. It will link with our water, it will link with all air conditioning and all those comforts and developments. At the same time, if we depend upon those extensively through burning of fossil and fuels, then it will lead to the release of greenhouse gases and leading to global warming. So I'll come to that aspect subsequently. But as you know now, the temperature has increased since second industrial revolution of 1880 to today, about 1 degree centigrade. And its projection.
Sir, your slide is not visible.
So if we go to future, then we'll see that the prediction that tells that by end of this century, the temperature will increase. If we keep as today, the level of greenhouse gases by 1.4 degree further. But if we go the way we have gone for last 50 years, from 1970 to today, then the increase will be as high as 5.8 degrees centigrade by end of this century. So such a change of temperature will lead to various aspects of the change in our Earth's climate system. And in fact, actually, as you know, that in this warming environment, we'll have weather extremes such as tropical cyclones, heavy rainfalls leading to floods, deficient rainfall leading to droughts, heat and cold waves, severe thunderstorms, and so on. The climate change is now most important issue before the scientific and politicians world over, and proper disaster management can reduce the loss of life. So there's a nexus among the climate, environment, and natural disasters, and they are so much interlinked that today the climate change, as we all know, it is due to the environment and ecosystems, because we have using excess of the greenhouse gases, which are these known as the pollutants. And these pollutants are the burning of fossil fuels, and also destroying our forests and green lands to develop the city, the industries, and so on. And ultimately, these things of global change or climate change will lead to the natural disasters, which is going to increase tremendously. And this natural disaster, as you know, can lead to a catastrophe in various sectors, and that is what we all are experiencing now. So therefore, foremost challenge before the humanity, if now we identify one, then it is the global warming and leading to the natural disasters. These natural disasters is, as we know, that it has a severe weather, that mainly actually it is two types. Natural disasters. One we call the hydrometeorological disasters, which involve hydrology and meteorology. They are generally cyclones, flood, drought, tornado, dust storm, heat waves, cold waves, and so on, many of them. Other than geophysical disasters, that is earthquakes, avalanches, landslides, volcanic eruptions. But if you see that hydrometeorological disasters are really more prominent, which contribute almost 90% of the natural disasters. And severe weathers refer to any dangerous meteorological phenomena with the potential to cause damage, serious social disruption, loss of human lives. According to climate scientists and meteorological community, the extreme weather events are mainly localized. Fortunately, they are not over the whole globe. They occur in localized regions. As you know, that it's like a thunderstorm, scale of few kilometers, or cyclone of few hundred kilometers. And also their occurrence is only 5%. It will not occur every day. It is only 5%. This is a record by World Meteorological Organizations. They have taken 10 years, 1991 to 2000, in which period they very extensively observed the different types of natural disasters around the world. And this shows the blue one is the hydrometeorological disasters, and the brick color one, geophysical. As you know, about 90% people that are affected are due to the hydrometeorological disasters. And the hydrometeorological disasters, as I have given here, starting from very small scale, tornadoes, fast floods, which are very localized, a few kilometers only, and time is half an hour to an hour or two, not more than that. To that of the droughts, which can be very large scale, covering larger region, and for the several days and months, even Sahel drought were for several years. So therefore, it is given in the arrangement of very short-lived to very long-lived. But these all are the known as the various type of weather and climate-related natural hazards. And the records show that if we have seen Tropical cyclone, they contribute to almost 30% of these hazards. Floods 32%, drought 22%. Almost 84% of natural disasters belong to hydrometeorological, flood, drought, and tropical cyclones. If you see the persons affected, then tropical cyclone 20%, flood 32%, drought 33%. Again, 85% people affected by 3 hydrometeorological disasters. If we see total number of reported disasters, then Asia stands as the number 1 with 43%, followed by Americas 23%, Africa 17%, Europe 14%. But if we see the loss of life that is due to disasters, Asia stands number 1 with 80%. Asia occupies only 33% of the world land mass, but accommodates 61% of populations. Most of the countries are developing countries, and all these and various factors lead to maximum casualty in this region. If we see the economic loss due to natural disasters, it is a survey by business today, and it is accumulated for last 20 years from 2000 to that of 2019. And you see that tropical cyclone, it is in the billions of dollars unit, figures in billions of dollars. Tropical cyclone, it is the largest in last 20 years. The loss is about $1,430 billion. Similarly, flood, second, $1,089 billion, which are almost half of our GDP of India that we lose in last 20 years due to tropical cyclone and floodings, and so also the other disasters. If we show, first I'll go to global warming to show you briefly some evidence of global warming, because up to 1970 and so, people are thinking global warming is just a rumor. People are not believing, because by that time, the global warming was only 0.5 degree to 0.6 degree in a period of more than 100 years. So therefore, it was whether really global warming there or not, it was debate. Then after that, concentrated efforts are done to see those things. And these show that from 1880, when we started using the coal as the source of our energy, to today, that is 2020, you can see that this is the global estimated based on land and ocean data. You can see that the temperature anomaly is monotonically increasing. The warmest years in recent years is 2016, 2019, and 2020. And if you go to today, it is 2022. This year, you know that we have also hottest year. That is what IMD declared. So this shows that global warming is there, and it is year by year, it will go on increasing. The sources of greenhouse gases, which is the cause of the global warming, because you will see that in Earth and atmosphere, Earth and solar system, in between in our atmosphere, if atmosphere we don't have, then our temperature would have been minus 18 degrees centigrade, global mean temperature. But the atmosphere, it behaves like a blanket. It protect and keep our atmosphere warm, because our atmosphere allows the solar energy to come in, but it does not allow all the radiated energy from our surface, a long wave radiation or terrestrial radiation, to escape from our Earth's surface. As a result, we are comfortably plus 15 degrees the global mean temperature. But if we are to increase this blanket with the greenhouse gases, then we have a surplus of energy which is coming from solar energy and not escaped. Then we get this type of gases is known as greenhouse gases, and that lead to the global warming and climate change. The main sources are almost 33% each: transportation, power generation, and agriculture and land use, land cover. If you see the global fossil carbon emissions, then the total, if we see petroleum, coal, natural gases, and cement production, all of these are major contributors towards this carbon dioxide, which is monotonically increasing since 1958 to today. If you see that it is go on increasing. And this, as I told, till now it is 1 degree in 130, 140 years. So it is very difficult to conceive that 1 degree change in 140 years means the 0.01 decimiller so the per year. So it is difficult. But therefore, nowadays, we are seeing different sources where actually change is felt. The black one is the downing, decreasing, white one is increasing. You see that 15 indicators univocally tells that it all are due to the global warming. Glaciers are decreasing, temperature over the ocean increasing, temperature over the land is increasing, sea surface temperature is rising, ice sheets are reducing, and so on. All these indicators indicates that we have a warming phase is going on. So therefore these changes have taken place. But then you know that Earth and the solar system and Earth system is such that we may have a natural change or maybe the man-made change. If natural, we cannot do anything. And it is due to the orbital motions of Earth around the sun and it is tilting. But it is a very long-term process. So now how will you know that whatever the change took place in this 140 years by what degree, whether it is man-made due to burning of fossil fuels or it is the natural. For that purpose only, we can take rescue of the modeling. And modeling is it is a highly computer expensive, and modeling a thing where actually transfer our science to the technology. That I'll come to you subsequently. So here actually we took several best models. The black line is the observations. The blue one is the natural and human factors. That means here we have keep the natural changes and we kept also burning of anthropogenic effects, forcing, that is man-made things. And the green one, that is only natural forcing, where we stop the anthropogenic forcing, that is the man-made burning of fossil and fuels. Then model is integrated for more than 100 years. And you see that if we use human factors, that is anthropogenic forcing, then it is follow the line, that of the line that is showing that the actual factors. But if we stop the human factors, that is the anthropogenic forcing, then you see that there's no increase. It is going a straight line. That means every year summer has a summer temperature, winter has a winter temperature, and it has no change. So that means it shows that whatever rising temperature anomaly is coming, that is due to the anthropogenic forcings only, and that is the burning of fossil and fuels, which I have told you earlier. And this is occurring globally, and also over the global landmass, and also global ocean also. So therefore, this anthropogenic forcing of human forcings influencing our entire global earth and land and ocean processes. So therefore, we have seen that it has impact of rising of sea levels, reduction in snow covers, and rising in the atmospheric temperature. Then its impact of climate change is very on some of the important sectors are our food security. It has large impact on the agriculture, hence food security. It has a tremendous impact on the water resources, because we have seen that Even we are lucky that during our monsoon, we get about 75% rainfall in India. The total rainfall, if average over India is 88 centimeter, unfortunately, our total rain is remain almost same, 88 centimeter. But we have the period of very heavy rainfalls for short time, leading to the floods, and long duration having no rain, leading to droughts. That means variability became large, so water resource is become a major concern with the climate change, which lead to food security. Climate change also, with the warming phase, it has impact on the health. It has an impact on the, it is due to clean energy, and hence it has impact on the sustainable development, and it's threat to the peace. Now I'll show the global warming and extreme weather events from observations. So this is a very simple diagram published in the Science in 2005, which shows different category of tropical cyclone. As you know, tropical cyclone, like human being, I show you details when I go to cyclone. It is generated as low pressure, depression, cyclone, severe cyclone, very severe cyclone, super cyclone. So the less intense cyclone we call category 1, medium range is 2 to 3, and very intense cyclone like a super cyclone or extremely severe cyclone, they're category 4 and 5. You see over the whole global basins, tropical basins where we have tropical cyclones, you see the category 1 is decreasing. But category 4 and 5, they are tremendously increasing. So that means this shows that the severity of the cyclone will be increased, and that is category 4 and 5, and whereas total cyclone may be decreased. This is the percentage which each basin, each because tropical cyclone, I will come subsequently, it is in the various basins of tropics, and one is our North Indian Ocean, and then Pacific and Atlantic, and also Southern Indian Ocean, we get tropical cyclones. But in all the basins, during 1990 to 2004 versus 75 to 89, you see the percentage of cyclones from common cyclone to severe cyclone percentage increasing. And you all maybe also experience from 2013 to today, we are getting many extremely severe and one super cyclone. So this is the North Indian Ocean, that is Bay of Bengal and Arabian Sea. So here actually I put low category, the cyclone in disturbances, very severe cyclone, the higher category. And here you can see that there is an increase of the category of very severe cyclones. And the percentage during post-monsoon is maximum about 59% increase of severe cyclone storms. And in the entire year, about 46% is increase in the severe cyclones compared to the cyclonic disturbances, which is marginally changed. If you come to the Bay of Bengal, North Bay, Central Bay, and South Bay, you see that South Bay, you see maximum change, that red line, which show that severe cyclones, US 50 years to current years, it is increasing tremendously. Similarly, if you see the Bay of Bengal between pre-monsoon and post-monsoon, which is depressions, cyclonic storms, and severe cyclonic storms, you see that in the pre-monsoon time, about 41% rise in severe cyclones. And in the post-monsoon time, about 72% rise in severe cyclones. So it confirms with the global picture also that with the climate change, the severity of the tropical cyclone is increasing. Same way, if you see the rainfall, over the India, particularly the central India, where we have get the rainfall, maximum rainfall during monsoon, then you see that the less amount of rain, that is the green one, less than 10 centimeter, 100 millimeter. Low to moderate events are decreasing, but more than 10 centimeter rising. That is heavy rainfall rising. Light to moderate rainfall is decreasing. Very heavy rainfall, more than 15 centimeter, also increasing rapidly. So this again signifies that during the monsoon, we have light to moderate rain is decreasing, heavy to very heavy rainfall is increasing. That leads to the floods, and that will be for the short period with the floods. Long time the drizzle or moderate rain is decreasing. So therefore, we'll have number of droughts will increase and number of floods will increase. Aggregate all in 122 days of monsoon, you will see that the total amount may be same. So this is again a finding of previous data. Flood catastrophe globally is increasing. Droughts are increasing. Events, windstorms, anti-tropical cyclone, and severe thunderstorms, extreme heat events, droughts and floods, all shows a increasing trend in recent years, and this is mainly due to global warming. Because due to global warming, increase of the land temperature and ocean temperature, our evaporation is increasing. So we are pumping more moisture to the atmosphere. That lead to holding capacity is increasing. So we get a heavy rainfall and then no rain. Because that is what is the consequence of this global warming. So the IPCC projection is that by the end of the century, the intense precipitation will be almost double, leading to a lot of floods and landslides and so on. Similarly, droughts will be also 66 to 90% will be rising by the end of the century, leading to the, again, agriculture production damage, hydropower city, wildfires, and so on. Tropical cyclones, again, increasing by 66 to 90%, and impact, as you know, in various sectors. So these major three hydrometeorological disasters are going to rise with the global warming. So therefore, tropical cyclones are either more frequent or more powerful. Floods, higher frequency. Drought, higher evaporation might induce more frequent droughts. Removal of vegetation reduces rains. Heat wave are increasing. Cold wave will be only decreasing. That is the only thing we get benefit. The cold wave will be less, and rest of the things are increasing. So therefore, now comes how we can protect from these disasters. As you know, application of weather and climate science in different sectors is enormous. Security, water resources, transportation, defense services, industry, clean energy, health, communications, tourism, and disaster management. In all these sectors, we have application of weather and climate. I don't have time to discuss each one. And the disaster have the various facets, and most important is that getting the information and giving the proper warning in time so that people can save their life. Because I do know, and I will demonstrate to you subsequently, that if we have timely warning and proper preparedness and mitigation strategy, we can save ourselves. And there where I will show you that how the technology developments have helped us. We can see major components of comprehensive disaster management system is the identification, observation, and understanding of the processes, improved impact-based prediction and warning well in time, risk evaluation and vulnerability assessment, all physical, social, and economic, effective dissemination, public awareness, and capacity building, disaster mitigation, adaptation strategy. You can see all these aspects are nothing but our marvels of our technology. Because only by technological intervention, we can tackle each of these aspects. and I will show you subsequently these things in my presentation. In India, we have almost all the disasters we face: flood, earthquake, cyclone, drought, everything that I told you. Risk management, early warning systems are developed. We have India Meteorological Department. They take care of earthquakes and meteorological hazards. Central Water Commission, they take care of floods. Geological Survey of India, landslides. Indian National Center for Ocean Information Services for tsunami live prediction. If we see the concept of weather observation, modeling, and prediction, then you see that our atmosphere is very, very complex. It has no boundaries. It is vertically and horizontally. Vertically, we have the lithosphere, where we have volcanic eruptions and earthquakes. It influences our biosphere and hydrosphere, and that linked to the atmosphere and all sorts of energy, the solar energy, that outer space. So therefore, lithosphere, hydrosphere, ice and glaciers, cryosphere, atmosphere, they are interactive, and they are extending the processes at different time scales. Therefore, the weather system is a highly nonlinear coupled system. The components of weather system are open and non-isolated. They interact on a wide range of spatial and temporal scales, and they are strongly coupled and are characterized by intense interaction at a various space. And along with that, we have the chemistry. We have in the atmosphere, we have the aerosols and various chemistry along with the water and solar energy. So therefore, in atmosphere, you know, the chemical interactions that take place, if you count their number, they are more than 1,500. That many interactions taking place because we have the different chemicals as aerosols, we have the water as a rainfall or water droplets or water vapors, and we have the energy from sun. All these make these chemical reactions. Here, you see that in the role of the technological developments. Now, to know the systems and understanding and prediction, we need a global Earth observing system, GOS. And it is a outcome of our knowledge in electrical, mechanical, and instrumentation science, because we use any new technology developed in the world, we use it immediately, like satellites, aircrafts, Doppler weather radars, unmanned aerial vehicles, UAV, lidars, ships, buoys, and so on. All these things we deploy to get observations, because about 75% area of our Earth are not accessible. Either they are the water bodies, which about 70%, or they are the deserts, or they are the glacier regions, or they are the mountainous regions where we cannot live and collect observations. Therefore, remote sensing observations are the best tool for taking the observation around the whole globe, and that is done by GOS, Global Earth Observing System, where technology is saving. Then, as I told you, that there is no boundary event, the Pacific or Atlantic. Today, after 5 days, it will affect the Indian Ocean. The cyclone coming to India, it may go to Bangladesh, it will go to Myanmar, it can go to Sri Lanka, or it may go to Pakistan or go to Oman. So therefore, there is no boundary, and it's a continuous process around the whole globe. So we need this data from various countries as early as possible, where data transmission is the most important thing. And in fact, as you know, within an hour, we get data of any country, whether it's United States or Australia or South Pole or North Pole. Anywhere data is collected within an hour in all the countries, including India. So their communication, electronics plays marvelous role. Once you get the data, data have to process it, and we have to integrate the model to get the result as fast as possible. And there, computer science and engineering and high performing computer is essentially used. And in fact, you know, the first computer when developed in 1948, it was used for the weather prediction. And now, also the largest computer that comes in the market, it goes for the prediction and climate prediction. And once you get the data, model, results, and effective warning, it have to communicate it to the end users, because they are the people who are going to suffer. So rapid dissemination of early warning system is equally important, and that is telecommunication. You know, in 1999, when we have super cyclone was there in Odisha, the then chief minister, he could not communicate with the rest of the people in Odisha and even come out of his house. That time only a few satellite-based communication system to Odisha to have a communication. But now we have that, and that is the rapid dissemination process through satellite is very important. And for these disasters, effective disaster management and mitigation is the most important. And now you will be happy to know India is in the Guinness book, because in 2013, Odisha, within 3 days, evacuated more than 1 million people. That is thanks to our government, Odisha Disaster Management and NDMA, National Disaster Mitigation Management Authority. They came to effect only 99. Odisha first started OSDMA, and 2005 we have started NDMA. And you know that we don't have shelters that time, and here civil engineering and management plays a tremendous role. We have now so many shelters around the coast, and now each village is linked with the so nice roads that we can evacuate the people. But it was not there 20 years. In 1999, we lose more than 10,000 people, and today in 2013, we lost only 20 people. I'll show you subsequently. And this is thanks to the civil engineering and management. And so all these things are our technological developments. And we have to see now how to arrange the climate change, how we can go to green environment. Here, most important thing to sustainable development that can keep our Mother Earth not to warm up. And that is possible only by the green energy and green environment. And it will be possible only again by technological marvels. That means we have to have non-conventional energy from the sources like solar energy, wind energy, hydroelectricity, and nuclear energy. You see that the solar energy, we are tapping only 11%. If we can tap 40% solar energy, then we don't want to buy fossil and fuel. That's a proverb there. The energy we are using today are the coal and petrol. And where from they are coming? They are coming beneath the earth. That means they are coming from the hell. But if we use the energy coming from the heaven, that is from the solar energy, wind energy, or energy coming from water as a hydroelectricity, they are a clean energy. They will keep our environment green also. And that is what our future strategy should be, so that we will cut down the release of greenhouse gases. And that will be possible only by technological developments alone. So that in future, we have to look for that, and that we have to start as early as possible. And now, as you know, all 198 countries, head of the states, they all sit together in Paris and various places subsequently, and making the how to reduce these greenhouse gases, and it will be possible only by the technical developments. Now let us go to that my weather science and climate prediction. As you know, this is science based on the observations. Because observations gives my understanding, because it is very complex nonlinear systems. And then we have to develop the nonlinear models, which have been integrated only by the computer, HPC, and then ultimately make a prediction and warning. Here, first thing is observations. As I told you already, remote sensing observations is the most important, and these are the different sources of taking observations from the balloons, aircrafts, radars, ships, and so on, and transmit that to one place. Again, weather and climate science is though it is known as science, it is engineering only, because it makes application of this science for the society. And that is what engineering. So it deals with the physical sciences, because all the laws, because it is a fluid, the atmosphere is a fluid on a rotating earth. So all these laws which make the models, they are based on the laws of conservation of physical processes like radiation, turbulence, convection, and so on. All these things have to formulate by mathematical sciences, because numerical analysis, partial differential equation, and fluid problems. Chemistry, I told you that a large number of aerosols and chemical things and chemical interaction and reaction in the atmosphere. If we write down those equations, they are more than 1500. Biological science plays a very important role, because evapotranspiration, albedo, Earth's roughness, they play a very important role. I'll tell you a little bit that subsequently. Similarly, earth science like lithosphere, cryosphere, soil characteristics, surface hydrology, they play a very important role in the water cycle of our planet Earth. Environmental science, air pollution, water pollution, ecosystem, as you know, they are responsible for restoring the balance of the atmosphere composition, and hence that is important. And to churn the model and to get your forecast as fast as possible, it is possible only by using the computer science. So now we have the large data mining, AI, ML, so on, and computer that all play a very important role to transfer these technological data collected platforms to that of the impact-based costs. If you see the development of the models for the atmospheric thing is not very old. It is only in 1960 we could first, because the computer first developed in 1948, as you know, as a result of the outfall of Second World War. We know that though World War is a wrong thing, or we lose many things, but we gain many technological developments like aircraft and computers are outcome of the Second World War. After 1948, we could be able to solve our problems with the computers, because nonlinear dynamics we cannot solve without a computer. So 1960, we started only as atmosphere. We thought it the only atmosphere is everything. Then 1980, we know that not atmosphere alone, it is land also plays a very important role. And 1990, we know that the ocean plays a very important role. So now we have the coupled models, atmosphere, land, and ocean. Then we saw that ice plays a very important role in 1990s. And in 2000, we came to know that carbon, sulfur, and others, and chemistry, they play an important role. So the history of the model developments is only 20, 30 years when we are coming to better and better models. And that's why you can know that whatever we are getting today improvement, that is because of the development of the models. And that is possible because of the observations and also understanding and computer simulations. So all these again as a result of our extensive technological developments. As you know, in 19 or up to 2000, it was very difficult to make a call, even to get a landline. Now everybody carrying in pocket 2-3 mobile phones, you can call to anybody anytime throughout the world. That is the communication developments. But in 2000, up to 2000, it was very rare. This is a complex modeling system. I will not take time to go through that for you. So this is how it shows that different things combined together to make a model which finally gives you the impact-based forecast of the extreme hydrometeor disasters. Here I am showing that in the skill forecast, one, we have the European Center for Medium, the weather forecast. It is the largest center in Europe, combined of all the countries of Europe. You see that if you increase the resolution of the model, which is possible due to computers, then our skill increases and we can better concept of a cyclone. We are in 1981, we are seeing cyclone like this way because we don't have enough computer. You said just a patch of cloud, but now we see that a cyclone having eye and having a spiral wind and so on. That is possible because now we can go into 16 kilometer global model and 0.5 kilometer the regional models. And that was not possible in 1981 because at that time we don't have that type HPC or supercomputer and so on. So this is the complexity of the model with different feedbacks and with dynamics, physics, water vapors, land surface, ocean, and so on. Again, I will not spend time, but this shows that different feedbacks that take place in the atmosphere to change our wind, temperature, humidity by various physical and dynamical processes. This is the different physics that it tracks. Again, I will not spend time for you. So this is the chemical sciences that's in the atmosphere, again due to aerosols that I'm telling. We have the carbon cycle, we have the nitrogen cycle, sulfur cycle, and oxygen cycle, and so on, and the hydrological cycle. All these cycles, the different processes that take place, and that govern our complex atmosphere. Even a plant that plays a role like radiation, energy balance, that is the surface albedo, water balance, evapotranspiration, rainwater interruption by the leaves, stomatal conductivity, that is photosynthesis, runoff, turbulent fluxes like roughness and because now you know that here we to stop wind of cyclones, we plant the trees. Why you plant the trees around the coastlines? Because when the cyclone is coming, there is a lot of wind due to the roughness, strong roughness of the plants. So it will dissipate there. So the land will not affected, people will not be so much affected. So this is how even the biosphere that plays an important role in our atmospheric processes. And this is again. I will go to show you some few examples. And here I will show an example of a tropical cyclone. So how much time I have? So tropical cyclone, hello, can you hear me?
We can hear you.
Yeah, so if we go to tropical cyclone, its characteristics is defined by these 5 things. The pressure drop, how much pressure, low pressure at the center. Maximum sustained wind, how much maximum wind at the eye of the cyclone. What is the radius of the maximum wind and what is the track of the cyclone and how much rain it is associated with. So these are the major characteristics of a tropical cyclone. This is a schematic of a tropical cyclone. The energy associated with a tropical cyclone, it is due to the large number of severe thunderstorms. And the energy, if you see that in the recent cyclone Amphan, if you calculate the energy associated with Amphan, it is equivalent to 1,500 atomic bombs that was used in Hiroshima and Nagasaki. That can clearly show you that how much enormous energy is there associated with a tropical cyclone. And where from it comes? It comes from the warm ocean, because ocean is the reservoir of the heat because of the large heat capacity, and it provides the energy to tropical cyclones. No tropical cyclone develop the land. It is only over the ocean. And it draws the energy from the ocean. The longer it remains in the ocean, it gets more and more energy that fuels it and makes it intensify. So therefore, all cyclones start with a low pressure, and if they are sustained enough, end with a super cyclone. Low depression, deep depression, cyclonic storms, severe cyclonic storms, very severe cyclonic storms, and super cyclones. They depend upon the pressure drop, which I told you is characteristic, and sustained wind speed. based on that, it is categorized as a different classical class as of cyclones. And we don't get cyclone alone in the Bay of Bengal and Arabian Sea, all tropical oceans, because for this minimum sea surface temperature is required, 26.5 degrees. And we have the cyclones in the, which we call tropical cyclones in the Bay of Bengal, Arabian Sea. That we call typhoons in the Pacific Oceans. We called it a hurricane in the Atlantic and Eastern Pacific Ocean. And also we have tropical cyclones also south of the equator in Indian Ocean. So these are the basins where we get the tropical cyclones genesis, and they are only in the warmer period of the phase because sea surface temperature should be warm enough to sustain a cyclone. If we see genesis, we get 80 to 100 cyclones around the world in a year. But our Bay of Bengal and Arabian Sea, they contribute only 5 to 6, only 6 to 7% of tropical cyclone, because our basins are very small basins. Maximum we get in the Atlantic and Pacific. Pacific is the number one, typhoons, followed by the Atlantic, and then we are the lowest category. But out of that, only 50% they are becoming intensified, as you know, to very severe cyclones. But we have only in our Indian basins, that is Bay of Bengal and Arabian Sea, we have two seasons of cyclones. Severe cyclone, STS is severe tropical cyclones. One is the pre-monsoon, this period, April, May, June, and other is the post-monsoon, October, November, and partly December. We have two seasons, but no other basin, not Atlantic, not Pacific, where actually we get about 90% of the cyclones, they have only one tropical cyclone season. But we have two, one pre-monsoon season, one post-monsoon season. It is due to the monsoon that we get in between from June to September. During monsoon time, we get maximum disturbances as a low pressure or disturbance, but not cyclones. Cyclone get pre and post. If we see the casualties, this is a record for the 300 years. And this record shows cyclones having more than 5,000 casualties in the period of 1700 to 2008. In that period, 24 events were there, and Bay of Bengal alone contribute 18. That is 75%. That means, you know, we have a very teeny basin. We have only 4 to 5% of global cyclone. The intensity is very low compared to the hurricanes in the Atlantic and typhoons in Pacific. But casualties of maximum casualties is 75% in the Bay of Bengal. And that is mainly due to the shape of the Bay of Bengal. And the storm surges. We have maximum number of rivers. You know, in Odisha alone, we have 6 major river systems. And all these rivers, delta region, low-lying area, and a funnel shape of Bay of Bengal. Bay of Bengal is like a funnel shape because it is more opening in the south and close in the north. So therefore, when the cyclone moves from south to north, as a characteristic of cyclone to move poleward, it always generates in the south Bay of Bengal or southeast Bay of Bengal and move towards northwest. That is a usual phenomenon. So all water pile up and all the river systems, we get very high storm surges, sometimes 12 to 15 meters. You know that infamous cyclone of 1970, more than 3 lakh people washed away in 1970 cyclone Bhola. But a recent one, 2008, the cyclone which crossed Myanmar, more than 1.5 lakh people are killed by the cyclone Nargis. So this is mainly associated with the storm surges. And this is actually Odisha, that is what we work out. if you see the same cyclone hitting Gopalpur versus Baleshwar, if hitting Gopalpur, it will give 4 meters of surge. But if same super cyclone hit the Baleshwar, it will give it 10 meters per 10 meters height of storm surface. You can imagine how it is distributed. So that means 10 meter water is coming means more people wash away in Baleshwar and Bhadra district than Ganjam if our same intensity cyclone comes. And if you see the total number of cyclones in distribution in 1901 to 2005, Odisha is number 1 with 101 cyclones, followed by Andhra Pradesh 68, West Bengal 65, Tamil Nadu 52. Again, our cyclone is not confined to India. India gets only 52%. We get cyclone going to Bangladesh, going to Myanmar, and going to also Sri Lanka. So therefore, as you can see that though it is a small basin, less number of cyclones, then it has a international thing. The uniqueness of our region that we get only 7% of world's total cyclone per year, but highest number of human deaths, casualty, that I have told you. We have 2 tropical cyclones, pre-monsoon and post-monsoon. Cyclones of relatively moderate intensity because they move only shorter period. A cyclone in the Pacific or Atlantic, they move for 7 to 10 days. But in 2 to 3 days or maximum 4 days, our cyclone cross the land. So therefore, it does not get enough time to gather the energy from the ocean. But certain segments of Indian coast are highly vulnerable to storm surges. That is due to the shallow bathymetry. As you know, like in Baleshwar, or you know that there, if you go to that coast, high tide to low tide, you can move 3 kilometers inside the ocean. Large stretch of low-lying delta regions with a cluster of islands and cyclone-prone east coast of India, where actually large number of river systems are there. Coastal population is very large, as you know, dense population because it is actually fertile lands, and ocean is there for the fishery and so many things. So that a highly populated region, and these are the main causes of highest number. And the processes of tropical cyclone already have told, I will not spend time. It has strong winds, storm surges, and heavy rainfall. All the 3 factors that lead to the large number of casualties. Real-time prediction of tropical cyclones, I will show you some figures. So I am showing you 2 models for Bay of Bengal and Arabian Sea. And now I'm showing that the improvement in tropical cyclone as a result of our understanding and a result of the computers. The left-hand side, the Odisha super cyclone of 1999, where the casualty is more than 10,000. It is government records. After that came 2013 cyclone. This is a prediction we have done from the IIT Bhubaneswar. You see that cyclone is predicted 3 to 5 days dot. Your white line is the observed, the red line is the predicted. And we predicted that 5 days in advance, the cyclone is going to hit between Gopalpur and Chilika. As a result, the OSDMA and the NDMA, they could evacuate 1 million people. That was Guinness record. And as a result, the casualty came down from a figure of 10,000 to 20. And that is what actually, as I told you, that is the technological marvels. That is what technology has given us to improve these things with the observations, modeling, computers, disaster management, and shelters, and so on, and communication, all these things as I told you earlier. So this is the real-time prediction of the cyclone falling 72 hours and 96 hours. And you can see the prediction landfall error is only 16 kilometers in 72 hours and 29 kilometers in 96 hours. So that is what tells that how accurately cyclone can be predicted so that people can evacuate. Then this is the intensity prediction, and it is a different world over various units. They have predicted the cyclones, and these are forecast errors. This is the rainfall. As you know, out of 20 people, actually 12 people they died in northern Odisha, that is Mayurbhanj and Baleshwar region, because of the heavy rainfall and floodings in Subarnarekha and Bodhabara, which was not predicted well in advance. And only 8 to 10 people died in the actual cyclone region. So this is the rainfall distribution, and you can see that rainfall cyclone cross here, rainfall maximum. This one we have not thought. We thought that here cyclone, here the rainfall, but rainfall maximum is in some other places. Like now you are getting rain in Odisha, but cyclone is already crossed South Andhra Pradesh. This is the storm surge associated with the tropical cyclone. It is also predicted 72 hours in advance. And this is a cyclone, another cyclone there, Lehar at that same time, which was decreased in intensity, and that is also very well predicted. This is the next year, that Mari, that is also that time, it has a recurvature that was also predicted, you can see. And this is the cyclone, all of you know very well, and that is your cyclone of 1999, Fani. This Fani cyclone, which cross of the land, you can see that it is predicted. It is also predicted 5 days in advance, 96 hours and 120 hours before. Every 12 hours, it is predicted. IMD predicted also, and we use this thing and develop this thing and give to IMD. And this all again, you see that these predictions, you see that all are telling that it is coming to land. And in fact, it came to land near Puri and passed through Bhubaneswar and Kataka and so on. And you know the damage. All of you know that about this cyclone. But it was well predicted. It was, genesis was around 27th April, and it crossed on 3rd May, and this is what the prediction. This is the intensity prediction. The black one is observed, and the red one is that predicted, and the right-hand side, the storm surges. So these all are predicted by the models, and this is the most recent 2020 super cyclone Amphan. Again, super cyclone Amphan was predicted 5 days in advance, and this is every 12 hours interval. And we have taken a couple models with hurricane watch, and another is a simple WR model. And every 12 hours interval we predicted. You can see the black one is observed, red one is predicted every 12 hours. It all shows a cyclone is not coming to Odisha, though it was expected by Odisha government to come to Odisha. But from clearly we have told right from this place that it's going to hit the Head Bay of Bengal and West Bengal, and that is what is happened, border of West Bengal and Bangladesh. The prediction with the coupled system, the red one, the forecast error, the coupled model HOR, you see that error is less compared to the WRF. So this shows that the coupling of land and ocean also improves the prediction. So I'll go a little bit about the severe thunderstorms, because now actually in India, the major threat is not tropical cyclone, though actually it is huge and lot of damage potential of a cyclone, but due to early warning and due to our disaster management and technological developments, the casualties remain almost 2 figures. But you know, in a year, the people due to lightning deaths in India is about 3,000. We lose about 3,000 lives every year due to the lightning associated with the severe thunderstorms. And it is very short-lived because it happens out 1 hour. It is very localized, 1 to 3 or 5 kilometers only, and then its warning is very difficult because being a small-scale process, very localized. It is warning is a difficult one, and it needs a lot of attention now, because the death is maximum now in the country due to natural hazards, the floods and severe thunderstorms. These two we are not decreased so far. And therefore, ground prediction of heavy rainfalls leading to floods and severe thunderstorms are the challenging problem for the community how to tackle. This looks like a thunderstorm, a tall clouds with a strong updraft and downdraft. And if a aircraft go inside, then it will be actually it will crash. This is a picture from the Doppler radars. A number of thunderstorms together lead to a squall line, and this is the radar for the Calcutta radar. And you see that it is about 500 kilometers, and you can see that this is a squall line that we can detect only by the Doppler radars, because ground-based observations it is not possible. It is neither remote sensing. The thunderstorm hazards are manifold, like cyclones. It leads to flash floods. If a thunderstorm occurs in a hilly regions like in northeast regions, most of the flash floods in the northeast India, in Assam, and in also Bangladesh, flash floods comes due to severe thunderstorms. And sometimes the city base, it has strong wind shear, so that it is a hazard for the aviation. It has a hailstorms which damage the crops. It has a lot of turbulence. You all may be experienced when a thundercloud is there and you go in the aircraft, you see that aircraft you can feel a lot of turbulence, and lightning, which is the maximum loss of life comes due to lightning. Some thunderstorms become severe, lead to the tornadoes and microbursts, and icing, which takes place with the aircrafts if they pass through these severe thunderstorms. This is the type of lightning that we get with the thunderstorms. Because this lightning, what happens, that there is a positive and negative poles, they are separated, and actually lightning can be cloud to cloud and cloud to ground. Cloud to cloud is not any important to us because it will only flash in the sky, you can get a thunder. But lightning from cloud to ground, it will lead to a lot of loss and casualties. Now the SOA University, as you know, they are predicting, Dr. Sahu, we have the now lightning detectors installed in Odisha. About 12 such lightning detectors are placed in various places where we have the major lightning there and thunderstorms, and to monitor that. But then it can also be predicted with the observations, and this is the hailstorms that is associated. And this is the prediction with the assimilation of the Doppler radar data with our models. Then you can see that squall line, which I was telling you earlier, and that is can be predicted. This is the rainfall that it comes, that can be predicted. And it can be predicted the drop in the pressure, certainly, and also drop in the temperature after the cyclone is well predicted. And wind speed increases, and then relative humidity increases, and with a thunderstorm. So all these things can be predicted. So I'll stop here because other things I'm not showing you because I think 6:30 and I should give some time to you. I conclude that the conclusion road ahead, global climate is changing, and this is apparent across the globe in a wide range of observations. The global warming of the past 50 years is preliminary due to human activities that we have seen due to burning of fossils and fuels. Challenges before us, reduction of greenhouse gases, as I told, use of green energy, solar, wind, and hydro electricity. I told you at the beginning, drastic reduction in burning of fossil and fuels, adaptation strategy in various sectors with minimum greenhouse gases, prevention and protection of environment and ecosystems. Some of the extreme weather events have increased in recent years, and new and strong evidence confirm that some of these increases are related to human activity. So impact-based warning system is highly important, which now IMD and others are working to have zero casualties. For zero casualty, we should need impact-based forecast. That means what will happen when we have some events occurring. And for this prediction, observation is the primary, and for observation, remote sensing is the primary. And for this thing, actually, we need technological intervention. Capacity building and public awareness, effective and timely mitigation strategy, management and adaptation strategy, all again effective disaster management. So with this, actually, I'll stop, and now I thank you all for your very kind attention to my lecture. So now you can ask me any queries you have. Thank you very much.
Thank you so much, sir. I would like to invite questions from the audience. If there is any question. Am I audible, sir?
Oh,
Yeah,
yeah,
yeah.
perfectly audible.
Sir, if there is no question, sir, I would like to ask a small question. Like, how does low and high albedo influences the climate change?
Yeah, you see that albedo because you see that the source of energy for our atmosphere
Right, sir.
is the solar energy. But solar energy, we call it short wave radiation because the radiation depends on the wavelength is inversely proportional to the temperature. Being sun's outer space temperature is about 6,000 Kelvin, so the wavelength is very small. So therefore, with that wavelength, our atmosphere is becoming transparent. Like our X-ray, our flesh is transparent, but bone is not transparent. Same way, the solar radiation is transparent for our atmosphere. It penetrates through. But when it penetrates through, maximum energy goes back as a reflection from the surface. It depends upon the type of surfaces.
Right, sir.
Like
Like
over the
if
snow,
it's having a dark surface, then we call it as a low
it will
albedo. Yeah.
Yeah, it is very low, means it will heat it up, it will absorb all the radiation.
Right, sir.
And if it is white surface, it will reflect all these things.
Right, sir.
So therefore, the snow cover, glaciers, and cryosphere, they play very important role. So also, as you told exactly, if we have more black bodies or more actually concrete roads and this tar roads and so on, then we trap more solar energy.
Yes.
So therefore, urbanization and cities, they trap more energy than our rural area where we have more plants and forest and so on.
Right, sir. Right. Thank you very much, sir. Over to you, Damodar, please.
Okay. Professor Nanda is there here?
Sir, is in another meeting, sir.
Okay, okay. So I have great pleasure in proposing a vote of thanks for our excellent speaker, Professor Charan Mohanty, and he gave an excellent speech and very illuminating it was, and very interesting to know so many things. I never knew that atmospheric modeling is actually so very complex, and the complexity actually came to the light here through this lecture. And also it gave some ideas that how we can manage it and how disasters are being managed and how climate change also could be managed. These are, I think, is a great thing. So Professor Mohanty, I am really very fortunate to listen to this lecture and learn so many things. And a great, actually, this is a good, thank you very much for such illuminating lecture. and particularly friends actually who could join. Their number was few, but they were also all through. I'm sure they would have really learned a lot, and thanks to them as well. So Professor Mohanty, I've got one request. This lecture is recorded. Can we really circulate with your permission?
Yeah, sure. No problem. You can circulate it.
Good.
Yeah.
So I think in this technology day, we have made it a day, and it is actually you who made it a day. Thank you very much.
Thank you very much, sir. Thank you very much for inviting me for this lecture.
ପରେ କେତେବେଳେ କଥାବାର୍ତ୍ତା ହବା?
ଆଜ୍ଞା. Thank you very much.
Thank you so much, sir. Thank you all of you for active participation and staying up last. Thank you so much, sir. Namaskar.
Namaskar.